Hey guys, I'm going to do the 2015 number 2, and let's just talk about it. To increase business, the owner of a restaurant is running a promotion in which customer bill can be randomly selected to receive a discount. When a customer's bill is printed, a program in the cash register randomly determines whether the customer will receive a discount on the bill. The program was written to generate a discount with a probability of 0.2. That is, given 20% of the bills, a discount in the long run. However, the owner is concerned that the program has a mistake that results in the program not generating the intended long run proportion of 0.2. So the owner selected a random sample of bills and found that only 15% of them received the discount. So a confidence interval for P, the proportion of bills that will receive a discount in the long run, gave plus 0.15 plus or minus 0.06. This guy here is called our margin of error. All the conditions were met and everything is great. So let's talk about just this right here. I'm sure most people said, okay, so 0.15 minus 0.06 is 0.09 and 0.15 plus 0.06 is 0.21. So with that being said, if we were going to write a conclusion for this, we would say we are we don't know how confident, but let's just say 95%. We are 95% confident that the true proportion of, I guess, bills or people that will receive a 20% discount or receive a discount is between, let me get rid of this, who will receive a discount is between 0.09 and 0.21. So that's what we would say. So we would say 95% confident that the true proportion of bills that will receive a discount, or the true proportion of people that will receive a discount, is between 0.09 and 0.21. So let's read the question. Does the confidence interval provide convincing statistical evidence that the program is not working? Well, the program is working. The program is working because 0.20 is a number that's in here. We have 0.20. That's a number that's in between here. So if you thought about it from like a hypothesis point of view, it's P equals 0.20, or let's say P does not equal 0.20. Well, it does, 0.20 lies in here. So no, because it said not working, there's so many double negatives. So no, since the interval contains 0.20, then we do have evidence that it is working as intended. So, or you can just say, the confidence interval does not provide convincing statistical evidence that the program is not working. So you could say not, or we can say that we do have evidence, since 0.20 is in there, that it is working. So now it says, does the confidence interval provide convincing statistical evidence that the program generates discount with a probability of 0.2? Justify your answer. It's so silly because it's kind of repeating itself, but does the confidence interval provide convincing statistical evidence that the program generates the discount with a probability of 0.2? Well, here's the thing with this. It can generate 0.9, 0.10, 0.11, 0.12, 0.13, and so on. It doesn't have to generate 0.2 exactly. It can generate any number between these two numbers. So sometimes it'll generate 0.11, sometimes it'll generate 0.25, 0.205, and so on. So it doesn't generate exactly 0.20. So in this case, we know the confidence interval gives you any values between these two. So no, it won't give you exactly 20, but any number between those two. So that's how you do letter A2. In this case here, it says a second random sample of bills was taken that was 4 times the size of the original sample. So let me show you guys something here. We know that this we know that it's like z sigma over the square root of n, or z, I'm going to rewrite this guy here so I can have 2. So we know that these are the margin of errors, okay? This is for when we have mu, this is for when we have a proportion. Look at what I did in this case here with this. I separated him. So if I did z over, let's say, 4 times, we know that since this is a monomial, that's equivalent to saying square root of 4 times the square root of n, which ends up being 2 on the bottom. If I had, let's say, 9 times the original sample, then it would be PQ over 3 times the original sample. Let me clear this up a little bit. So what happens here is that if we multiply a sample by 4, you're dividing the margin of error by 2. If you multiply a sample by 9, you divide the margin of error by 3, and so on. If you multiply the sample by 25, you divide the margin of error by 5. Remember, when you multiply the sample, it's getting larger and you're getting closer and closer to the true mean, which means the margin of error needs to get smaller and smaller. So it says determine the value of the margin of error based on the second sample that would be used to compute the value of P with the same confidence interval. So the second random sample of Bill's was taken that was 4 times. So remember that in the past problem, it was 0.15 plus or minus 0.06. And this guy here is our margin of error. Multiplying it by 4 means divide him by 2. So the new margin of error is 0.03. So that's how we get that guy. Now it says, based on the margin of error in part 3, what do you conclude about whether the program is working as intended? Well, now instead of 0.15, let me erase some of this. Now instead of 0.15 plus or minus 0.06, it's 0.15 plus or minus 0.03. That gives us 0.12 to 0.18. Now, 0.20 is what they wanted. It's not in this. It's in the rejection region. So the interval does not include 0.20. And so there is convincing evidence that it is not generating the discount of the probability of 0.20. Remember, it's giving us any number between 0.12 and 0.18. So it's not generating 0.20. And that's basically how you do this problem.